Hey, it's Moser with a quick video on the behavior of ions in aqueous solution and colligative properties. That said, we are not going to talk about colligative properties at all. So this is really more about ions in aqueous solution. And as a matter of fact, it's mostly just writing net ionic equations. So let's call it that. Okay, so really, what I'm building you up for here is a later skill that will benefit you if you go on in chemistry, which is understanding how acids and bases behave and form ions in aqueous solutions and then interact. And to get you to a point where that's really easy, we're going to work on the current skill, which is writing net ionic equations. Now, to be able to write net ionic equations, there are two foundational skills that you're going to master, and they're really quick and easy. The first one is dissolution or dissociation equations. The second one is predicting solubility of ionic compounds. So those are the two foundational skills that we're going to build and then put together to do writing net ionic equations. Cool, let's go. So first you need a vocabulary word, and that vocabulary word is dissociation. When ionic compounds dissolve in water, and we've seen this repeatedly with models of the behavior of ionic compounds in water, the ions actually separate. That is what we call dissociation. And we can show this using what's called either an ionic equation or a dissolution equation or a dissociation equation. So here we see that solid NaCl, sodium chloride, yields aqueous sodium ions and aqueous chloride ions. And the atoms, the number of atoms on each side of the equation, are balanced, as are the charges. Let's look at one example together, a little slightly more complicated one. Okay, I lied. First, let's talk about the stoichiometry of dissociation. So if we have 1 mole of sodium chloride, how many moles of sodium ions will that yield? And how many moles of chloride ions will that yield? 1 mole of sodium chloride, once dissolved in water, yields 1 mole of sodium 1+ ions and 1 mole of chloride 1- ions. So it seems counterintuitive that a single mole of sodium chloride can yield 2 moles worth of ions, but that's the way it works. Let's practice that. If I had 1 mole of barium nitrate, BaNO3 2 times, dissolving, how many moles of barium ions and how many moles of nitrate ions would I yield? Well, I'd yield 1 mole of those barium ions, Ba2+, and 2 moles of the nitrate ions. Note that this number is coming from the subscript in the original formula for barium nitrate. We show this by writing a dissolution equation or an ionic equation or a dissociation equation. Any of those will do. So here's what I'm showing. BaNO3 2 times in the solid form yields Ba2+ in aqueous solution plus 2 NO3 1- in aqueous solution. Now, notice that the number of ions, or the number of atoms of each type on each side of the equation is balanced, and I've included state information. That's really important. Okay, let's practice one more. I've got 1 mole of ammonium sulfate dissolving, and so I know that that yields 2 moles of ammonium 1+ ions, 1 mole of sulfate ions. Now, it's important to note that a dissolution equation or ionic equation just shows that one compound here, the ammonium sulfate, and the ions that it dissolves into, the ammonium ions and sulfate ions. Okay, good. Now, leading up to our goal of being able to write net ionic equations, we have to be able to predict solubility. This is our second foundational skill. So if you're using the Physical Holt textbook, on page 427, you will find this chart. If you are using the PDF of a different version, chapter 13 in the PDF on page 437 has this chart. So what we're going to use is these solubility guidelines, and these give us compounds based on their components. So we talk about sodium compounds, potassium compounds. We also talk about things like nitrates. So that would be compounds that include a nitrate ion. It's general guidelines and, possibly more importantly, exceptions to those guidelines, specific exceptions. So let's practice. We're going to begin with the first one on this list, ammonium nitrate. So as I look at these guidelines, guideline number 1 says that sodium, potassium, and ammonium compounds are soluble in water. Okay, so based on the fact that this is an ammonium compound, it should be soluble. But I'm going to keep reading to make sure there are no specific cited exceptions. Rule number 2 says nitrates, acetates, and chlorates are soluble. Hey, this is a nitrate. Double whammy. This thing is certainly soluble. So now let's look at ammonium sulfide, NH4 2 times S. Well, the first rule, sodium, potassium, and ammonium compounds are soluble in water. Well, this is an ammonium compound, so that's a check. Okay, this is soluble, but it's really important to keep reading and look for exceptions. Ammonium sulfide, nitrates, acetates, and chlorates are soluble. Well, this is none of those. Most chlorides are soluble except for blah, blah, blah. This isn't a chloride. Most sulfates are soluble except those. Well, this isn't a sulfate. Most carbonates, phosphates, and silicates are insoluble except, well, this is not a carbonate, phosphate, or silicate. Most sulfides are insoluble. Oh, except those of calcium, strontium, sodium, potassium, aha, and ammonium. Hey, double check mark. This is another yes. Awesome. Let's do one more together. But do you see how important it is to look for those exceptions? Calcium carbonate, sodium, potassium, ammonium compounds. Nope. Nitrates, acetates, chlorates. Nope. Most chlorides. Nope. Most sulfates. Nope. Wait, most carbonates are insoluble. Hey, this is a carbonate. So while I don't have any particular rule for calcium compounds, I do have a general rule for carbonates. And sure enough, calcium carbonate is insoluble. You can do the last two on your own. Okay, so now we want to look at precipitation reactions. This is where we're getting closer and closer to our net ionic reactions. If we have two ionic compounds, both of them in aqueous solution, that we mix, and if a double replacement reaction can occur, which results in an insoluble compound, what we're going to see is the formation of a precipitate. By using our rules for solubility and our ability to write dissolution equations, we can predict what precipitate will form, if any will. We'll run through the process quickly, and then we'll do it in a little bit more detail. So, to do the prediction of a precipitate, we'll take the example of ammonium sulfide and cadmium nitrate. So, for the NH4 2 times S, the ammonium sulfide, we're going to write the ionic equation or dissociation equation for each of those compounds. So I know that ammonium sulfide as a solid will give me 2 moles of ammonium ions and 1 mole of sulfide ions. I know that cadmium nitrate, CdNO3 2 times, will give me 1 mole of cadmium ions and 2 moles of ammonium ions. Excellent. Now I'm going to write an equation as though a double replacement reaction will occur. So I've got ammonium sulfide in aqueous solution plus cadmium nitrate, also in aqueous solution, yields cadmium sulfide, question mark on the state information, and ammonium nitrate, also question mark on the state information because I don't have that yet. Then I have to look up the solubility or the predicted solubility of those potential products and put that into the equation. So what I find is that cadmium sulfide, in fact, is not soluble in water, while ammonium nitrate is quite soluble in water. Based on what I have found then, I'm going to say that the cadmium sulfide will precipitate out, but the ammonium and nitrate ions are just going to stay there in solution. They're going to remain dissociated. Now, to get to the point of writing a net ionic equation, we already did this step where we wrote a dissolution or ionic equation for each of those. We already did the step where we figured out which potential products were soluble and not. And then what we have to look at is which ions are just standing around not doing anything. Well, we know from our last slide that the ammonium and nitrate ions don't form a solid compound. They stay dissociated. Any ions that don't form new compounds are what we call spectator ions. They're just standing around watching everybody else do stuff, not doing it themselves. We cross those out to get to our net ionic equation. So when we take the ammonium sulfide aqueous plus cadmium nitrate aqueous and get cadmium sulfide solid and ammonium nitrate aqueous, we do this whole big ionic equation. This shows all of the ions from both of those compounds that we started off with and the products, both the ones that form a solid and the ones that will remain in aqueous solution. We cancel out any ions that are still in aqueous solution on both sides of the equation. What we're left with is a net ionic equation. So we get cadmium 2 plus in aqueous solution plus sulfide 2 minus in aqueous solution gives us solid cadmium sulfide. Let's try one from scratch. So I have sodium chloride in aqueous solution and silver nitrate also in aqueous solution. I want to know if there will be a reaction that forms a precipitate, and I would like to know which ions just spectate. So I'm going to start off by writing my dissolution or ionic equations for the dissolution of the dissociation rather, of each of these compounds. So I've got solid sodium chloride gives me 1 mole of sodium ions and 1 mole of chloride ions. Solid silver nitrate dissolved in water gives me 1 mole of silver ions and 1 mole of nitrate ions. Great. Now what? Well, now I want to write an equation that looks like a double replacement reaction. What are my potential products? Well, sodium could pair with nitrate, and the silver could pair with the chloride ions. But I don't know if either of these things is soluble. Aha, I need to pull out my solubility table. Okay, well, sodium compounds are soluble and nitrate compounds are soluble. So the sodium is definitively going to be soluble. That's a check. Let's see. Chloride compounds. Most chlorides are soluble. Wait, except those of, silver. Silver chloride is not soluble. So I am going to have a solid precipitate. Now I can go ahead and finish that double replacement reaction, putting the state information in, noting that the ammonium nitrate is going to stay in aqueous solution, while the silver chloride will precipitate into a solid. Now I'm ready to write that big, messy, overall ionic equation. So I show a mole of sodium ions, a mole of chloride ions, a mole of silver ions, and a mole of nitrate ions. The sodium and nitrate stay in solution while the silver chloride forms a solid. How does that look when I cancel out the spectator ions? Well, it shows chloride and silver ions reacting to form silver chloride. That is my net ionic equation. And when you're doing these, you do want to both show this and this net equation, so you do need to rewrite it. That's it. This should help you as you move forward in chemistry, looking at ionization of acids and bases. If you have questions, just ask.